In this video, we're continuing to talk about lines, planes, and distance. Last video we talked about lines. Now we're going to talk about planes. In particular, we're going to talk about the fact that a plane is determined by a point in the plane and a vector normal or perpendicular or at a 90-degree angle to that plane. We're going to derive the standard form of the equation of the plane, and we'll also talk about the general form. And then we'll sketch some planes and show how our sketches relate to points in the plane and normal vectors. So one thing I wanted to point out is the similarity or the parallel between lines and planes. Now we said earlier that lines are determined by a point on the line. So that's our point P, and then some vector that's parallel to the line. Planes are similar. We need one point in the plane to distinguish it from all of the other planes. But instead of finding a vector that's parallel to the plane, we need a vector normal to the plane or perpendicular to the plane. If we have those two things, that's going to be enough to determine a plane completely. So let me just draw a little cartoon of our plane. Got something that looks like this, let's say. And here is a point x naught, y naught, z naught in the plane. That's given to us, generally. And let's say we also know a normal vector to the plane. It's n. And please note that I crossed this out just because I wanted to do it in a different video. We're going to talk about this first, and then we'll go back to that in a little bit. So I've got a normal vector, and I've got a point x naught, y naught, z naught. That's given to us. We can describe this plane similarly to the way we were describing lines earlier. The plane is the set of all points x, y, and z. So here's just a general point x, y, z, such that this vector from x naught, y naught, z naught to x, y, z, let's call this P and that Q. The vector from P to Q, it's not parallel to n this time. PQ always has to be perpendicular to n. It always has to be orthogonal to n. It always has to be at a 90-degree angle from n. Some people might say it's not at a 90-degree angle. Well, it is. It's just drawn over there. It's the same thing. It's just drawn in a different place. This vector n is parallel to, or is perpendicular to all of the vectors in the plane. Or we should say, because they're vectors, this vector n is orthogonal to all of the vectors in the plane. So we're looking for a set of points x, y, z, such as this vector from P to Q, where P is given, is orthogonal to the normal vector n, also given, and we'll assume that it has components a, b, and c. So I need PQ to be orthogonal to n. Remember what that means. When are two vectors orthogonal to each other? When do they meet at 90-degree angles? What operation do we know that tells us two vectors meet at a 90-degree angle? I hope you said dot product. I really do. If these guys are orthogonal to each other, then PQ dotted with n has to be 0. And let's work that out a little bit more. What is PQ? Well, PQ is a vector from P to Q, so we'll take the coordinates of the terminal point and we'll subtract the coordinates of the initial point. So we have x minus x naught, that's our x component, y minus y naught, that's our y component, and z minus z naught is our z component. And we're dotting that with the vector n, which has components a, b, and c. And we're going to know those. theoretically. Suppose we know the normal vector and x naught, y naught, z naught. Well, that dot product has to be 0 because those two vectors are orthogonal to each other. Let's work out the dot product. We've got this times A plus this times B plus this times C that is called the standard form of the equation of the plane. Okay. Now, if I take that equation and I rearrange it a little bit, if I distribute the A and I distribute the B and the C, I can rewrite that in a different form. I've seen textbooks do it different ways. We'll have AX plus BY plus CZ. Some of them put plus D equals 0 and call that general form. Some of them say all of this equals D, and that's general form. And that's fine. Just really depends on the textbook. D is that A times x naught plus B times y naught plus C times z naught. A, B, and C are known. X naught, y naught, and z naught are known. So this is just a number that comes from distributing the A, B, and C and then moving all those negative terms to the other side. So this is called general form of the equation of a plane. And sometimes you see in other books it's written this way. In that case, D is a little different. I'm going to write it as like D star. D star is negative A times x naught minus B times y naught minus C times z naught. It just depends on whether you keep the constant on the left of the equal sign or the right of the equal sign. Some people say that's general form and some people say that's general form. Okay, so let's practice. Let's say you've got a plane, or you're given a normal vector, and that normal vector is 2, 3, 6. And you're told that the point let's say 4, 2, 1 lies in the plane. Given normal vector this and point P that lies in the plane, we make sure it says given this normal vector and P, I'll just say that lies in the plane. Somebody might ask you to find the equation of the plane. EQN is my abbreviation for equation. In standard form and general form. It's actually very easy. Standard form looks like this. A, B, and C. Those are the components of your normal vector. Those go out front. So you're going to have a 2, a 3, and a 6. And x naught, y naught, and z naught, that's what you subtract from the x, y, and z. So you're going to subtract a 4, and subtract a 2, and subtract a 1. So this is your equation in standard form. Or if we distribute the 2, distribute the 3, distribute the 6, and let's add those constants to the other side. We've got 2x plus 3y plus 6z equals, the other side we're going to have 8 plus 6 plus 6. So it's 12 and 8, which is 20. Oops, it's off the screen. I'm sorry, guys. Here we go. This is general form, or one of the general forms. And that's it. Now, if someone gives you the equation of a plane, someone might ask you to find a normal vector, the normal vector to the plane, or a normal vector to the plane, and a point P in the plane. So let's talk about that a little bit. So let's say we're given that our plane has equation. Let's just do something simple. X plus y plus z equals 6. Let's say you're asked to find the normal vector. Oops. Or actually, let's be more precise, and I'll talk about why. I should say it this way. Find a normal vector to the plane. And a point in the plane. Or on the plane. It's actually very, very easy. Remember, A, B, and C, those are the components of our normal vector. Those go right here, here, and here. And remember why that is. Let's go back to this page. Because we were taking the dot product of the normal vector with this vector PQ from some representative point in the plane, or from some given point in the plane to some representative point in the plane. So when you took the dot product, that ABC ended up right here. That ended up being the coefficient of the quantity x minus x naught, and then y minus y naught, and then z minus z naught. And so we're doing that. And then we distributed and we collected like terms of the constants, and we moved the constants to the other side to get general form. Question is, how do you find the normal vector? That's right there. That's your A, your B, and your C. After you distribute, the coefficient of x is your A, the coefficient of y is your B, the coefficient of z is your C. So in our case, the coefficients are 1, 1, and 1. So that's enough to give me my normal vector. So my normal vector is the vector 1, 1, 1. Or if I was doing this one backwards, the normal vector is given by the 2, the 3, and the 6. So my normal is 2, 3, 6. Okay. Now if somebody asks you for a point in the plane, there are lots of points in that plane. I mean, we're talking about a plane, and this is just a cartoon. Oops, that doesn't look normal. That looks like a 90-degree angle. We're talking about a plane that is normal to, or perpendicular to, or at a 90-degree angle from this vector 1, 1, 1. There are lots of points in that plane. Lots of different points that will all work. How can you find one of them? Well, it's just like algebra class. What if I gave you y equals 2x plus 3, and I said, find me one point on that line? You just plug in x equals 0 and you get y equals 3. So 0, 3 is on the line. Say, okay. Or if I plug in x equals 1, what does y have to be? It has to be 5. That's on the line. Or if I let y equal, let's say, y equals 7, well then 7 equals 2x plus 3. If I subtract 3 from both sides, I get 4 equals 2x. So x has to be 2, right? So we're at the point 27. What did I do to find all those points? Well, I just picked one of them and then figured out what the other one would have to be. Now, this is very similar, but we've got 3 free variables here, or excuse me, 2 free variables. If I pick 2 of them, the third is defined by this equation. So if I want some points in this plane, I'm just going to choose, let's just say x and y are both 0. If x and y are 0, then z has to be 6. So the point 0, 0, 6 is on the plane. Similarly, if x and z are 0, y is 6. And if y and z are 0, x would have to be 6. Say okay. You always have to choose 0? No, you can pick anything you want. You could do 100. And then, I don't know, minus 94. And then z is 0, so you get 6. You could do 2, 2, 2, because 2 plus 2 plus 2 is 6. Or 1, 1, and 4, because 1 plus 1 plus 4 is 6. All of those are in the plane. So you choose 2. So you choose the value of 2 variables. 2 of those are free variables. You can pick them into anything you want, just like we've got 1 variable free here. And the third is determined by the equation of the plane. Okay. Alright, so on this one, let's say I'm trying to get 20. How can I get 20? Well, 1 point on the plane, if let's say z was 2. Or actually, let's say z is 3. Then 6 times 3 would be 18, right? So I chose z equals 3. And then I just need 2 more points. So let x equal 1. So then I'll have 6 times 3 is 18. 18 plus 2 is 20. Then y would have to be 0. So the point 103 is on that plane. Now that's not the same point we started with. 4, 2, 1 is also on that plane. But if you can find any x, y, and z that satisfy this equation, that x, y, z is in the plane. You get a lot of points here. Just a ton of points to choose from. But just like in algebra, if it satisfies the equation, it's on there. It's on the plane or on the line. Okay. So, okay, what does this all mean? Well, we were talking about this idea earlier. This line is determined by the fact that it has this point and it's parallel to this vector. Now there are plenty of other lines that are parallel to that vector. That was not quite parallel. I mean, they could be closer together. It doesn't matter. But those are all determined by different points. P1, P2, P3. Guess I could use a different letter, R. Whatever. Those are determined by different points. But if I have 1 point and that vector, well then that's enough to distinguish that line from all the other lines. That vector gives me a family of lines that all point in the same direction. But to pick out the right member of the family, we need a point. Something similar is happening here. There are a bunch of planes that all have the same normal vector. to decide which plane you're on, you need a specific point. Just one point. You don't need all the points. Just one point on the plane would be enough to distinguish that plane from all the other planes that are parallel to it. But vectors or planes that have the same normal vector are all parallel to each other. That number d, when we look at this equation, this number d on the right-hand side being different means the plane is actually different. A, B, and C, if the A, B, and C are the same, that means the planes are parallel to each other, and D is going to move that plane. It's going to shift it. Let me show you a little bit more specifically what I mean. So let's say we want to graph this plane. I've been drawing a lot of cartoons for you. I'm like, oh look, here's a plane. You're like, okay, I'm just drawing this little square and it's supposed to indicate a plane, but it actually goes on forever in all of these directions. It's infinite. It's this infinite 2D flat surface. That's what we're talking about when we talk about a plane. You might say, okay, Miss Townsend, how can I visualize that particular plane? Well, one way we can visualize that particular plane is to graph the part of the plane in the first octant. So this is a question that comes up a lot, a problem that comes up a lot in exercise. They might say, graph the part of the plane in the first octant. That's actually pretty easy. We're going to do something similar to what we just did. With this equation, if I choose two of the variables, the third variable is determined by the equation. To figure out where our plane crosses the x-axis, the y-axis, and the z-axis, I can set two of these variables equal to 0 and see what the third one would have to be. So our plane will cross the x-axis when y and z are both 0. So if y and z are both 0, we get 2x equals 20. 2x equals 20 when x equals 10. So this is not to scale, but it crosses here at 10. And then you say, okay, well, when does it cross the y-axis? Well, then you let x and z equal 0. Well, it turns out it's going to cross that y-axis when 3y equals 20. 3y equals 20 when y equals 20 divided by 3. What's 20 divided by 3? It's a little less than 21 divided by 3, right? So it's a little bit less than 7. But I'm just going to write 20 over 3 right here. This is not to scale. And then for z, let x and y be 0. So these guys are gone. And now you've got 3z equals, or 6z equals 20. So z equals 20 divided by 6, divide that one by 2, divide that one by 2, and you get 10 over 3. It's half as big as that. So it's a little bit more, that's 3 1/3, right? So it's right there, approximately. Not to scale, the whole thing's not to scale. So our plane passes through those 3 points, and I can draw it like this. Now, we imagine that it continues beyond this little patch. It's going to go beyond, it's going to go behind the YZ plane and behind the XZ plane and below the XY plane. But the part that we see in the first octant where X, Y, and Z are all positive is that part. You'd say, okay, what does that tell me? Well, then it's really hard to see here, but coming out of this plane, I'm just trying to show you, it's a little bit hard to see from this perspective. It's like you're in physics class, right? And you draw that little dot. The vector is coming out at you, and that vector has components. The normal vector has components 2, 3, and 6. Okay, you may say, how is that different from a different plane with a different right-hand side? So it's a very good question. I'm going to change the right hand side now. So let's make the right hand side, let's make it 12. Actually, I think I want to do it with a different plane because this plane is so small. Let's do this very simple plane. I've got x plus y plus z equals 6. That one's very easy to sketch very quickly. Let's make it a little bit more interesting. Let's put a 2 there and a 3 there, just for giggles. Okay. And I will try to draw this one a little bit better to scale. Alright. If y and z are both 0, we have 2x equals 6, so x equals 3. You divide both sides by 2 and we get x equals 3. If x and z are both 0, we get y equals 6. And if x and y are both 0, we have 3z equals 6, so z equals 2. Okay, and so this is what our plane looks like. This is the part of the plane that we can see, the part in the first octant. Now it continues. It goes beyond this. It goes below the xy plane. It goes behind the yz plane. It goes behind the xz plane. So remember what we talked about with this being like the wall to the left of you, this being the whiteboard behind you, and this xy plane being what you're standing on if you're looking at the class from the origin, if you're standing right here and then looking out. So this is like going into the next room, and that's going into the room behind you. And then this part of the plane, that's going downstairs. So that's this purple part. Okay? What if instead of 2x plus y plus 3z equals 6, we had 2x plus y plus 3z equals 12? Oh, I'm gonna need a lot more room for y, aren't I? Y is gonna go all the way out to 12. Okay. See what happens? If I double that number on this side, if I change that 6 to a 12, well, now I've got a new equation. When y and z are both 0, we get x equals 6. When x and z are 0, we get y equals 12. And when x and y are both 0, we'll get z equals 4, because 3z is 12 when z equals 12 divided by 3, or 4. I'm trying to make those lines straight. I'm not doing a very good job. Okay. So this red plane, it's a little closer to us than that purple plane, but they're parallel. So as this number increases, it looks like that plane is getting closer and closer and closer to us. If this was a 3, well, then I think we'd be back here. If this was 3, when x and y are 0, when x and z are 0, y is 3. If x and y are 0, we get z equals 1. And when y and z are 0, we get x equals 3 divided by 2. That's 1.5. So we see, I'm not drawing very straight lines. Do you see that that's parallel to this one? and it's behind the purple plane, and the purple plane is behind the red plane. And so as this number, as this d increases, it's getting closer and closer and closer to us. But they all have the same normal vector. That normal is pointed in the same direction for all of them, which is given by that 2, 1, 3, the coefficients of the x, the y, and the z. One other just terminology piece. This line where the plane intersects the xz plane, the red plane intersects the xz plane, or the xy plane, or the yz plane, these lines are called traces. A trace of some surface in the coordinate plane, in one of these coordinate planes, say a coordinate plane, is the curve where that surface intersects the coordinate plane. So this red plane, that was the one with the 12 on the right hand side. If I want the trace of this plane in the xz plane, sometimes we might call it just the xz trace. Well, in the xz trace, y is 0. So you set y equals to 0 and then simplify. So we have 2x plus y, which is 0, plus 3z equals 12. So our equation of the trace is 2x plus 3z equals 12. So we just got that line right there. Okay. And then if I want the yz trace, that's where x equals 0. Well, if x is 0, we just get y plus 3z equals 12. I'm just covering it up because it's gone. It's 0 now. And then the last plane, the xy plane, so we're going to look at the xy trace. We're going to set z equal to 0 because z is 0 down here. It's floor level. If z equals 0, we get 2x plus y equals 12. More about planes, just a couple of other special planes that you might want to sketch. If you have x equal to a constant, and you want to know what that looks like. X equals 0 is back here. That's the YZ plane. So if you have x equal to a constant, say x equals 3, it's parallel to the YZ plane, but it passes through x equals 3. So I'm trying to make it clear that it passes through there, like that's on the plane. Okay, but this is parallel to that. Like if this is our classroom, and that's my whiteboard, and here I'm standing here, x equals 3 is 3 feet in front of me. It's the plane that's parallel to the whiteboard behind me. If y equals a constant, remember which coordinate plane that's parallel to? Now remember, y equals 0 is back here. If this is me in my room, and I'm standing here looking at you, to the left of me, y equals 0 is that left wall. You've got the whiteboard behind you and all that. If y equals a constant, we're talking about a plane that's parallel to that wall, or parallel to the xz plane. So let's say we have y equals -4. So that's -1, 2, 3, 4. And I'm going to try to draw a plane that goes through y equals -4 that's parallel to this one. It's hard to do. But it passes through that point down there in the on the y-axis, y equals -4. And this was supposed to be x equals 3. Sometimes we just do the best we can and then we just label it. So that's supposed to be x equals 3. That's supposed to be y equals -4. And of course, z equals a constant is parallel to the floor in the classroom. The floor, you know what I mean. Here's z, here's x, here's y. The xy plane is what I'm standing on. It's z equals 0. Z equals 4, or let's do z equals 3. It's just 3 units up. It's up here. Oops, there you go. Okay. Now sometimes someone will say, oh, give me a plane that's parallel to the YZ plane that passes through a certain point. There are a couple of different ways you could do that. If I tell you that it's parallel to the YZ plane and it passes through, let's say, -1, -3, 5, well, I know if it's parallel to the YZ plane, it's just x equals a constant. So the equation should be x equals whatever that coordinate is of the point that's in the plane. So it'll be x equals -1. Another way to do this, I think it's a harder way to do it, but it's another good thing to think about. Another way to do it is to think about the normal vector of this plane. What vector is normal to the YZ plane, guys? You actually got 2 of them. I mean, you've got infinitely many of them. But probably the easiest one is I hat. Isn't I hat, that unit vector in the x direction, parallel to that plane that has x equals a constant? Or I said parallel. Perpendicular to that plane or normal to that plane where x equals a constant. It's definitely meeting it at a right angle, right? So the normal vector to all of these planes is, or one normal vector is 1, 0, 0. Now I keep saying the normal vector and then changing my mind and saying a normal vector instead. The reason I'm doing that is because I can make this any length I want. Yeah, 3i is just as orthogonal to that, or 3i is just as normal to that plane as 1i is. So is -2i, -200i. You know, anything times I is going to be normal to these planes. We usually try to pick the one with the smallest integer. So I would just choose the normal vector 1, 0, 0 here, I hat, for a plane that has x equals a constant. Notice I'm using the x component here. I've got a non-zero x component when the equation is x equals a constant, because the x axis is perpendicular to that. Okay, so what if y equals a constant? Well, what's the normal vector there? Well, there are lots of them again, but the normal vector here is just j hat, so 0, 1, 0. That would work. Again, if I told you that we're talking about a plane that is parallel to the xz plane and passes through this point, well then I immediately know that y is equal to a constant. If it passes through this point, well then y is equal to -3, so that'd be the plane y equals -3. So it'd be just like in between here, be in between those two guys. Or if it passed through that point and z was equal to a constant, the equation would just be z equals 5. Well, what plane would that be? If that's z equals 3, 2 units up, we've got z equals 5. And what's the normal to that plane, guys? I hope you see that it's just k hat. So 0, 0, 1. So you might want to keep that in mind as you're doing these problems. If I see the equation of the plane like this, I can just read off the normal vector. It's given by the coefficients of x, y, and z, or its components are the coefficients of x, y, and z. But if they ask you some questions that are more geometric, they say it's perpendicular, or it's parallel to this plane or perpendicular to this other plane, you might have to think about it a little differently. You might have to draw some pictures and visualize what's going on. But this will always be true. Any plane that is parallel to the x or the yz plane is x equals a constant. Parallel to the xz plane is y equals a constant. And parallel to the xy plane is z equals a constant.